At a large distance r from a radio antenna, the intensity of the radio signal I is related to the power of the signal P by the formula above. For the same signal emitted by a radio antenna, observer A measures its intensity to be 16 times the intensity measured by observer B. The distance of observer A from the radio antenna is what fraction of the distance of observer B from the radio antenna? To summarize the problem, there is an antenna and it sends a certain signal with a power of P, and the intensity of that signal depends on where somebody stands. We have two observers and one of them measures this intensity to be 16 times stronger than the other. And from the common sense approach, we can probably understand why. That observer has to be standing closer to the antenna, and that's why the signal would be stronger. We are offered a mathematical formula describing how the intensity works. The intensity I equals P, the power of the signal, divided by 4 pi r squared. R, as we know, is the distance. It is in the question in the first sentence. We can safely assume that the power of the signal P does not change for both observers A and B, that it is the same source. And we also know that the distance is probably involved. They are standing at a different distance, R. And we also know that 4 is a number and it doesn't change, and pi represents a number and it also doesn't change. And pi stands for a number of 3.14 approximately. If we were to pick a lazy approach and eyeball the formula, we'd identify that the only changes happen in the intensity of the signal I and the distance r. And we can see that since the difference is 16, everything is explained by the distance, and the way distance impacts the intensity of signal is that in a squared form, it would actually explaining all the difference. And if r squared and the difference in signal strength is 16, then we could predict that r would equal 4 in this case. Scanning the answer choices would find 1 over 4, and that would be a lazy and intuitive way to solve this problem. But we wouldn't have maybe the same level of confidence in this. But sometimes when facing time pressure, that may be one approach you would choose to pursue. If we were to stick to the process, then we'd have to take quite a few steps to arrive at the answer. We know that the intensity formula is P over 4 pi r squared. We also know that the intensity measured by observer A is 16 times that measured by observer B. So we can set it up as I for intensity of A, observer A, equals 16 times I for observer B. Now let's set up the intensity for both observer A and B. It would be for observer A, P over 4 pi r of A squared, because in this case we're taking the distance that the observer A is standing at. And the intensity for observer B would be P over 4 pi r of B squared. And r of B stands for distance of the observer B. So the only difference would be at the distance that both observers stand. And now using this formula combining with the one we came up earlier, we can see that P over 4 pi r squared A, or the intensity of observer A, equals 16 times P over 4 pi r squared for B. And in this case, it is 16 times the intensity that observer B measures. Let's now zero in on the RA and RB, or the distance of observer A and observer B. And one way would be for us to get rid of the more constant pieces of the formula, which is P over 4 pi. We can divide both sides by P and multiply by 4 pi. That would lead to cancellations for both P on both sides and for pi on both sides. And what we'd have left would be 1 divided by RA squared. And that would equal, on the right side, we have 16 times 1 divided by RB squared. Now we'd prefer both distances in the squared form to not be in the denominator. So let's try to address that. Let's multiply both sides by RA squared. And RA squared would be canceled out on the left side, and it would appear on the right side. So what we get in this case is 1, which is everything that's left on the left side, equals 16 times. We have RA squared in the numerator and RB squared in the denominator. Now let's also do the same for RB squared and try to get it out of the denominator form. And to do that, we would move it to the left side by multiplying both sides by RB squared. That would cancel it out on the right side, and it would appear on the left side. Finally, since the question asks us the distance of observer A in terms of observer B, let's also move 16 to the left side. This way we will isolate the distance of observer A, and we do so by dividing both sides by 16, which cancels it out on the right side. And 16 appears on the left side of the equation in the denominator. So our setup is RB squared divided by 16 equals RA squared. We are interested in RA in terms of RB, so this whole squaring gets a bit in the way. So let's reverse the operation of squaring by taking a square root of both left and right side. And if we do that, we are left with RB over 4. Square root of RB squared is RB, and the square root of 16 is 4. So RB over 4 would equal square root of RA squared would be RA. So we get this setup finally, which is RA equals RB over 4. Let's read the question one more time. The distance of observer A from the radio antenna is what fraction of the distance of observer B from the radio antenna? If we look at the answer choice A, we see 1/4 as an option, and we should be able to recognize that RB divided by 4 equals RA is the same as 1 divided by 4 times RB equals RA. And this kind of form makes it very obvious that our answer choice is A, 1/4.